Hello everyone again. This is lecture number 4 on the chapter Units and Measurements. Today we will be starting with the significant figures and then move on with the further discussions such as dimension analysis, etc. So I'm Samir Lawankar. Let's begin our discussion. Okay, so first of all, a course outline for you. So we started with the introduction first of all, then we understood the SI units. So basically, why was there a need to understand the SI International System of Units? And the next thing was based upon the measurement of length. Then next, in the measurement of length, we understood two different concepts. One was based upon your what we can say measurement of very large distances, and second was measurement of very small distances. In the measurement of very large distances, we understood the concept of parallax method. Okay. The next was measurement of mass, in which we understood what is basically SI unit. SI unit is kgs, and one thing more which we understood was that what is the atomic mass unit, that is U, that is denoted by U. Okay. Next thing was based upon the measurement of time is done. The next was accuracy, precision of instrument and error in instrument. This was being explained in the last lecture only. So this was based upon how what is three different concepts were being understood. First of all, we understood what is error. What were the two types of errors, basically systematic errors and random errors. What are some of the few ways in which we can reduce those errors? Then we understood three formulations, basically relative error, absolute error, and percentage error. We also did some of the examples, questions regarding this sixth subtopic. In this topic, we also understood one other concept called as your a combination of errors, right? So in combination of errors, we understood how the error has to be explained or measured for a quantity, which is, let's say, summation of two quantities having errors, difference of two quantities having errors, then product of two quantities having errors, division of two quantities having errors, and another is that if the quantity to be measured is in some power, such as example z is equal to a square, or in general we can say that it is, let's say, z is equal to a to the power x into b to the power y upon c to the power z, let us suppose. Then how to find out the error associated with the value of z? Basically, we need to calculate the value of delta z. So simple formulations have been done regarding that also. That is like delta z is equal to delta a plus delta b. That is for subtraction and addition. And for multiplication and division, it is delta z by z is equal to delta a by a plus delta b by b. Similarly, let us say if we are finding out for a to the power x into b to the power y upon c to the power z, then that delta z by z will be equal to x delta a by a plus y delta b by b plus c delta c by c z z times delta c by c. Okay, so that was the end of the complete course outline and the revision of all the things which we did in the last three lectures. So let us start today's lecture with the significant figures concept. Okay, so let's start with significant figures. Okay. As you can see, as discussed above, every measurement involves error. So in the previous all the lectures, we have understood this concept that everything which you try to measure always has some error involved in it, right? Now that those error, how to basically convey that error, or basically how to write that error is it involves a principle, or it involves a methodology in which we adopt scientifically, which is called as significant figures. Okay, now let us say okay, significant figures has to be understood now. So let us start. Let me just first iterate everything, and then we can move on to the further discussions. Some rules are there for significant figures. What is basically this concept? We will try to understand first. Okay. So as discussed above, every measurement involves errors, quite evident. Thus, the result of measurement should be reported in a way that indicates the precision of measurement. Very important. So please remember this line. Please understand this line very evidently. So let's say example, I will try to convey this using an example. Okay. So let us say my example states that let's say we have a device. Let's say this is let's say there is a device. Let's say I'm making a black box only. Let us say this is a device which is used for measurement of length, right? Now this device, after measurement of length, what does it do is it has a resolution of let's say 0.01 centimeters. Okay, what does it mean? That the answers which will be obtained from this device will be, let us say, the examples would be what? The examples can be, let's say, 1.42 centimeters, or let's say 6.96 centimeters, or let's say 5.00 centimeters, or let's say 4.50 centimeters. So this will how we will try to put or show the answer. Why? Because it has a resolution of 0.01 centimeter. That means, let us say we got the answer as 4.5 centimeters, right? But actually, in physical terms, to be very very accurate and go with unison with everything which is regarding the rules of significant figures, you never report the answer as 4.5 centimeter. Always the answer is reported as 4.50 centimeter. The only and only reason why we do it, because so as to follow the concept of significant figures. Because there are two significant figures, therefore it's quite evident, or therefore it's quite necessary to report the answer as 4.50 centimeters and not 4.5 centimeters. Okay. Now this thing is done. So basically, what does it tell? So basically, this tells you the precision, right? This tells you the precision with which an instrument can measure the answer, right? Let us go with one more detail. So let me up this everything and let us start again. Okay. Let us say the true value of a quantity to be measured is, let's say, we should I'm ignoring the units for now. You can take any units. Let's say the answer is 6.96523. Let us say now I have some device 1, I have some device 2, I have some device 3. Okay, let us say the first device cannot measure decimal points. No decimal points can be measured here. Okay, let us say the resolution of the second device is 0.01 and 0.01 units, whatever be the units. And let's say the resolution of device 3 is 0.0001 units. Okay. So what we can understand first of all from this, that the precision of this is the lowest, then so basically this is less, then the precision of this, and the precision of this is highest. Fine. So this is the first concept which we can understand after looking at the resolutions of all these different devices. Okay. Now basically what will happen? So the answer 1, 2, 3, 4, 5. Right. So the final answer which this device, let us say I write one more zero here. Right. So the answer which it will finally say, if everything is correct, that is there is no error or uncertainty involved, and the final answer which the device 3 will convey to you will be 3.96523. Similarly, but this time the device 2 will convey you the answer as 6.97 only. Why? Because it has a precision only up to the 0.01 units. Similarly, for the device 1, the answer would be obtained as 7 units. Now you can see the difference in the answers. The difference in the answer is much more higher. So significant figures also involves the concept of your rounding off. So that thing has already been done. But finally, what I need to explain is you can just look at the answers. So let us suppose you know the procedure of finding out the significant figures and rounding off. And final answer which can be used as an output from these devices are this value. Okay. So it is quite evident that the device 3 is having a very higher strength, or is very much crucial for the what we can say for finding out more accurate results, right? So this is a complete concept, or why we involve with the concept of significant figures, and why we look at more precision alongside accuracy. Accuracy is important, but precision also makes a very important concept in our day-to-day life. Okay, so 7 units is basically, as you can see, the error with this is very very higher as compared to this, and error in these both is very very much higher as compared to this. Okay, so let's move on with the now iteration part. Okay, so let us read this everything which is written here. Okay, so as discussed above, every measurement involves errors. Okay, thus the result of the measurement will be reported in a way that indicates the precision of instruments. Quite evident. So that was the only concept which I tried to explain to you right now. Now, next thing is that normally the reported measurement of error is a number that includes all digits in the number that are known reliably plus the first digit that is uncertain. Okay, so what does this line tries to tell you? That the final result which you obtain, it includes all digits, but there are some numbers which are reliable or certain, and there are some numbers which are uncertain. What does it try to mean? Let us say that the measured value is, let's say, 4.56 units, right? Here these two units are certain. This is an uncertain quantity or uncertain number. Okay, so that was the only explanation which was been done here. So the normally a reported result of measurement is a number that includes all digits in the number that are known reliably plus the first digit that is uncertain. Okay. Now next thing is the reliable digits plus the first uncertain digits are known as significant digits or significant figures. So this is one of the explanation or definition of your significant digits or significant figures. Okay. So the reliable digits plus the first uncertain digit. Okay, reliable digit, please remember anything which is written after 4.56, after 6 basically, let's say it's written 4.563 or 4.5632, right? Those numbers 3, 2 are uncertain as because 6 is uncertain. So anything which we write after this will be surely uncertain only. We don't know, we are just predicting the values. Or if we are finding a range, in which they must lie, but they are not certain values, right? Therefore, what the concept says is because everything which is in our 6 is uncertain, we say that we have defined something called as significant digits. Those only those digits will be called as significant digits that include certain digits plus the only the first uncertain. Okay, so that was the definition. Let's move on then. The next line states that if we say that the period of oscillation of a simple pendulum is 1.62 seconds. Okay, now let us try to understand these examples clearly. Okay, so we are right now on this point here. So if we say that the period of oscillation of a simple pendulum is 1.62 seconds, the digits 1 and 6 are reliable and certain, but or while the digit 2 is uncertain. Thus, the measured value has three significant figures. Okay, try to understand these concepts very carefully because this is only the main part or main crux of this complete chapter. Okay, so let us say I will try to explain the question again or the concept again. So this is basically your certain and this is basically your uncertain. Okay, always the last digit is uncertain and it is being called that certain plus uncertain digits are called as significant figures. In this case, which will be equal to 3. Okay, fine, let's move on. Why 3? Because there are two certain digits and one uncertain digit. Okay. Let's move on to the next example now. The next example states that the length of an object reported after measurement is 287.5 centimeters. Okay, so as you can see, 287.5 centimeters. Okay, so here in 287.5 centimeters, you can see clearly that the first three digits are certain and the last digit is uncertain. Certain plus uncertain is equal to 4. Okay. So it is just written that it is 4 significant figures. The digits 2, 8 and 7 are certain and digit 5 is uncertain. Okay. Next thing says that clearly the reporting the new result of measurement that includes more digits than the significant digit is superfluous and also misleading since it would give a wrong idea about the precision of the measurement. Quite evident. Let us say for example, the measured value came out to be 2.63 meters. Okay. Why it came out to 2.63 meters? Because the resolution of the device was 0.01 meters. Now let us say that the experimental not the experimental value, let us say the true value was 2.63 0.639 meters. Okay. As the last digit was uncertain, you would have put any value here. Let us say you would have put one value, right? Because it is uncertain, you can see the difference in the error which can be observed between 2.631 and 2.639. So because it is uncertain, addition of anything here is already there is a higher probability or higher chances that anything you add after the first uncertain digit will be erroneous only. That's why it is suggested that you should only and only provide the answer or provide the solution or provide the research as far as the resolution of the device is considered and significant figures rules are being intact. Okay, fine. So let's start with the next point here. The next point states that the rules for determining the number of significant figures can be understood from the following example. Okay, so let us look over the example, whatever is written here. Significant figures indicate, as already mentioned, the precision of measurement, which depends on the least count of the measuring instrument. So I think I have explained this concept several times, that the resolution is basically, or the instrument is basically the least count of the measurement. Okay, so significant figure can be predicted based upon the least count, if the least count of the devices given to us are known. Okay, let's move on then. Next thing is, a choice of change of different units does not change the number of significant digits or figures in a measurement. Okay, so even let us say, so this explanation is just saying that, let us say there is a concept 4.52 meters. Okay, if I change this meter to centimeter, the amount of significant digit does not change. The significant digits are same even after conversion. Okay, so just keep that in mind. Okay, some of the examples are being kept in the subsequent slides. You will understand this concept much more clearly there. Okay, so a choice of change of different units does not change the number of significant digits or figures in a measurement. This important remark makes most of the following observations clear. So let us see what are those observations being talked about here. Let us see. Please look out to the explanations clearly, because then it will be very easy to understand this complete concept. Okay. So let's see. So first example is, for example, the length 2.308 centimeter has 4 significant figures. Okay, so we will keep on practicing the concept, and then it will be easy for us to understand. Okay, so 2.308 centimeters. Okay, so this thing is certain, this thing is uncertain. Certain plus uncertain is equal to 4. Okay, therefore this is having 4 significant figures. Fine, this thing is explained. Next thing is, but in different units, the same value can be written as 0.0308 meters or 23.08 mm or 23080 micrometers. Okay, all these numbers. Okay, I think there is no confusion in how these things came, right? So we should remember simply that 1 centimeter is nothing but equal to 1 upon 100 meters. First thing. Second thing is, again, 1 centimeter is nothing but equal to 10 mm. Right, and as 1 meter is nothing but equal to 10 to the power 6 micrometer, you can just convert it based upon the explanation or answers here. Okay, fine. So this thing is explained. Next thing is that what you need to do is now. Okay, so this thing is explained. Let's move on. So all these numbers have the same number of significant figures. So digits 2, 3, 0, 8, namely 4. So as you can see, everything has so these are the only 4 digits which are significant. Okay, this shows that the location of decimal point is of no consequence in determining the number of significant figures. Okay, you should just remember that, yes, if it is given that there are 4 significant figures, just start from the leftmost position, just start from the first number, and all those digits will always be significant. What does it mean? What it basically means, I will try to imply. What does it mean? It just simply means that with 100% certainty, you know these 3 numbers. With uncertainty, you know this number. But in all, you know all these 4 numbers which are called as significant figure. Okay, there is uncertainty, maybe uncertainty regarding things which are written outside this, right? But there is no uncertainty regarding this values. There may be uncertainty regarding this 0 value here, but there is no uncertainty regarding all the 4 digits which you have conveyed here. Okay, there is uncertainty regarding last 8 is uncertain, but as significant figures are being asked, therefore you need to convey it also. Okay. Okay. So all these numbers are same number significant figures, namely 4. So this shows that the location of decimal point is of no consequence determining the number of significant figures. Okay. So this thing is so this example gives us the following rule. What is the rule here? All these numbers have the same number of significant figures. So this is explained. So the rule states that all the non-zero digits are significant. Okay. So this is the rule, that all the non-zero digits are always significant. Okay, so let's say 1 to 9, everything is significant. Okay, so that is the first rule. Some rules are like you can always predict, or you can always intuitively predict that yes, this is a rule, but they are just stated here so that everything is in written form and we can understand from the rules also if we have a confusion in the future. Okay, fine. So all the non-zero digits are significant. Next is all the zeros between the two non-zero digits are significant, no matter where the decimal point is, if at all. What does it mean? Let us say, for example, we take this case into scenario only. So 2.308 centimeters. The line just states that, as first rule states that all the numbers which are non-zero, so anything which is between 1 to 9 will always be considered as a significant figure. So using this first rule, we can say that 2, 3, 8. So basically 2, 3 and 8 are significant figures because 0 is there. The second rule states that if there is a zero lying between two non-zero digits, right, or two significant digits, as you can see that if the zeros, all the zeros between two non-zero digits are significant, that means this zero is also significant. So from here we got 3, from here we got 1, hence total this is equal to. One thing more which they are trying to imply here is, let me again iterate. So they are trying to imply, let us say we write 0.02308 meters. Okay, here this zero is under significant figure, but these two zeros are not under significant figures. Okay, so don't make a mistake here. There is no use of finding out a decimal value. Generally, examples are such that we need to find out that we need to take one number from the left hand side, or the complete number from the left hand side, and all the digits on the right hand side. But generally speaking, in physical terms, in scientific terms speaking, there is no rule in which there's a usage of decimal point when we are trying to find out significant figures. Okay. So this thing is explained. Next thing is, if the number is less than 1, okay, the zeros on the right side of the decimal point but to the left of the first non-zero digits are not significant. Example is already written here. So in 0.002308, the underlying zeros are not significant. So these are the basic underlying zeros here. Okay, as this is the first non-zero digit, so these two are not significant figure. Okay, moving on. The terminal or trailing zeros in a number without a decimal point are not significant. Okay, what do they try to say? The example is written here only. What are trailing zeros? Basically? So let us say here 123 meters, right? So 123 meter can also be written as 123.00 centimeters, which can also be written as 123 ml. So I think there would be no, it's fine. Okay, so as you can see, if you see only this, just ignore the right hand side for now. If you see only this, it is quite evident. From here we can say it is having 3 significant figures, right? One way we can understand this concept is that you should know, yes, we know that we have a rule which says that even without changing the units, there is no effect on significant figures. So from that rule, so we can correctly say that the second number in centimeter and third number in mm will also have the same number of your significant figure, that is equal to 3. But just to imply that rule again, or just to strengthen that rule again, we have written we have imposed one more rule. That rule states that all the trailing zeros without a decimal point are not significant. Okay, so if there's a trailing zero, let us say, so these are trailing zeros only basically. So this time what happens is, because there's a no decimal point explained here, therefore what we need to do, we need to ignore these in the significant figure. Okay, let us say this is the question we asked. Okay, so this time the amount of zeros will be from this, right? It won't be that you need to, because they are trailing zeros, you need to ignore them. So that is one of the things which you need to remember. So here total significant figures will be 1, 2, 3, 4, 5, 6. It will be 6 significant. Okay, fine. So this thing is explained, this thing is explained, this thing is explained, this thing is also explained. Moving on, so just explaining whatever is written here. So thus 123 meters is equal to 12300 centimeters, which is equal to 123,000 mm, has 3 significant figures only. The trailing zeros being not significant. Okay, fine. However, you can also see the next observation. So what is the next observation? The trailing zeros and a number with a decimal point is significant. Just the explanation which I just explained to you using the example has been written here. So the last line says that the trailing zeros in a number with a decimal point are significant. What does it say? Let us say we are writing the numbers like this or numbers like this. So it is having 4 significant figures. Why it is having 4 significant figures? Because first of all, the zeros are on the right hand side of the decimal, right? And it is being written till that point, okay? Because it is a decimal point. If there is no decimal point, then it is for certain that you don't need to add or use those zeros in significant figures. But if there is a decimal point, you need to use those values. Okay, so here it's 1, 2, 3, 4, and here it's 1, 2, 3, 4. Okay. Okay, so these won't. Okay, just 1 minute. Here it will be 1, 2, 3, 4. Here it will be 1, 2, 3, 4. Okay. So that is how you need to understand this concept. Fine. So this thing has also been explained. Let's move to the next point. Let's go to second point here. Second is again an example only. So let us understand this example now. There can be some confusion regarding the trailing zeros. Okay, let us try to understand this concept again. Suppose a length is reported to be 4.700 meters. Okay, so let us keep on writing. You also make a habit to keep on writing everything and you try to understand the significant figure concept, because it will be much more easy to understand this concept again then. Okay, so this thing is given that suppose a length is reported to be 4.700 meters. It is evident that the zeros here are meant to convey the precision of measurement and are therefore significant. This is very, very important point, right? This is very, very important point. I explained you this concept when I was trying to understand you in the black diagram also, in the black slide also, that there was an experiment being done, but because the precision of the instrument was 3.550, therefore we added 0 here, right? 3.5 is not the answer. The correct answer to be rewarded is 3.50 units. Whatever be the unit, been explained there. Okay. So therefore, as the question was 4.700 meters, so here the amount significant figures will be 4. Okay. It is evident that the zeros here are meant to convey the precision of measurement and are therefore significant. Okay, if these were not, it would be superfluous to write them explicitly. The reported measurements would have been simply 4.7 meters. So this was the only concept which we were trying to imply. Okay, now suppose we change units. Now let us change units. You know the answer very well. Let us say we have converted it into 4.700 meters, 470.0 centimeters, 4700 mm, and the next is 0.004700 kilometer. Okay, since the above last number has trailing zeros, as you can see there are trailing zeros here. In a number with no decimal, we would conclude erroneously from observation 1 that the number has 2 significant figures, while in fact it has 4 significant figures, and a mere change of units cannot change the number of significant. Okay, so basic crux again is this only, that you need to remember this rule, that there is no effect of change of units on the number of significant figures. Okay, fine then. So this thing is explained. I think there is nothing to explain here more. Let us try to go to the third example. Okay. To remove such ambiguity in determining the number of significant figures, the best way is to report every measurement in scientific notation, that is in the power of 10. Okay, so there may be some ways or some confusions when we try to find a number of significant figures. So the best way which people found out or the researchers found out was that to signify everything or report everything in the terms of scientific notations. Okay, so what is scientific notation? That is being explained here. So in this notation, every number is expressed as a into 10 to the power b. Okay, let's say I have a number that is 4. So 4 can be expressed as 4 into 10 to the power 1. If I have a number, let's say 36, then 36 will be expressed as 3.6 into 10 to the power 1. Okay, okay. Further things are explained in the next lines only. So let us first iterate and then I will try to explain using examples. Okay. Fine. So in this notation, every number is expressed as a into 10 to the power b. And a is a number between 1 and 10. So this you should remember. A is always a number between 1 and 10. And b is any positive or negative exponent or power of 10. So b can be any positive or negative exponent or power of 10. Okay. In order to get a approximate idea of the number, we may round off the number a to 1 for a less than equal to 5 and to 10 for a lying between 5 to 10. Okay, so for now you can just try to understand. If you are trying to understand this, very good, but if it is a little bit confusing, you will understand it when the examples are being explained. Okay, so this line just states that if, let us say, for some case or another, the value of a is going greater than 5, let's say it's going 6 into 10 to the power something. So what we do is we try to reduce it again, and we round up number to 1. Okay, how that rounding off is done, there will be several examples in the subsequent slides. I will make sure that you understand this concept. For now, if it's okay, then please understand it as a fact only, and then we can try to understand in subsequent slides. Okay, next line states that the number can be expressed approximately as 10 to the power b, in which the exponent or power b of 10 is called the order of magnitude of physical quantity. So this term of order of magnitude will be used in even 11th class, 12th class, even if you opt for any higher studies. Everything will involve order of magnitudes. So please understand this concept carefully, because it is one of the part which is being explained or which is being used in the higher studies also. Okay, so what is order of magnitude? Order of magnitude is basically to understand that basically the power of b is called as the order of the magnitude of the physical quantity. Okay, so when only an estimate is required, the quantity is of the order of 10 to the power b. Okay, so we don't look at whatever the number which is on the left hand side. Let's say something multiplication is being there. We just look at what is the value being obtained of the power 10 to the power something. What is that order? So we can understand from that only that what is the range in which we are working on. Okay. So that thing has also been explained. Fine. So this thing is explained. This thing is explained. This thing is explained, and this thing is also explained. Okay. For example, the diameter of the Earth is 1.2 into 10 to the power 7 meters. Okay, so a very beautiful example has been explained here. Is of the order of 10 to the power 7 meters with the order of magnitude 7. Okay. So what does it say? Let me try to explain it using an example. So what is the basic strength of order of magnitude, right? So let us say order of magnitude. Okay, so let us say some device or some object has an order of magnitude of, let's say, 10 to the power 5 meters. Let us say some device another has a order as 10 to the power 1 meter. And let us say there is a third thing which has an order of 10 to the power minus 15 meters. Okay, so just by looking at the order, we can understand or we can predict a device which could be used for the measurement of such quantities, right? You won't use a ruler meter scale and go on measuring this 10 to the power 5 meters, right? You cannot go and use a vernier caliper or even a meter scale or a parallax method to measure such very small orders, right? But you can use a meter scale here. So that is the concept which we are trying to understand. So if we are going for prediction, or if we need to take some instrument from, let's say, point A to point B, in which at point B we need to measure something, then beforehand, if we at least know the order of magnitude, we can take the suitable devices and then perform our experiments. Okay, so that is how, or that is the basic one of the agenda, one of the example of how order of magnitude is useful in our day-to-day life. Fine. So one of the examples written here. So for example, diameter of the earth is 1.2 10 to the power 7 meters, is of the order of 10 to the power 7 meters. Quite evident, as you can see, 10 to the 7 is written here. Therefore, the order will be 10 to the power 7. With the order of magnitude 7. Okay, so the order of magnitude is 7. Okay. Next thing is the diameter of the hydrogen atom, that is 1.06 into 10 to the power minus 10 meter, is of the order of 10 to the power minus 10 meters. Quite evident. With the order of magnitude minus 10. Thus, the diameter of the Earth is 17 orders of magnitude larger than a hydrogen atom. So, what they just did, they did 10 to the power 7, I want 10 to the power minus 10. Nothing else. Okay. That is how you can find out one thing is how much times greater than the other in terms of, let's say, length, time, or let's say mass, anything, temperature, etc. Okay. Fine. Next thing is said that it is often customary to write the decimal after the first digit. Now the confusion mentioned in A above disappears. Okay. So what we are trying to do, so basically let us say we take this as an example. Let us say we are writing 4.700 meters is equal to 4.700. So how we are writing it? We are just writing 4.700 into 10 to the power 2 centimeters. So because this thing cannot be changed, so we are just ignoring the statement, right? Similarly, we can also write this as equal to 4.700 into 10 to the power 3 mm. Similarly, we are writing this as equal to 4.700 into 10 to the power minus 3 kilometers. Okay. Okay, next slide states that the power of 10 is irrelevant to the determination of significant figures. Quite evident. There is no use, we just look at these quantities and we can find out what is the answer. Okay. However, all zeros appearing in the base number in the scientific notation are significant. Each number in this case has 4 significant figures. Okay, so first of all, you should remember that this time the significant figures is not based upon the trailing zero or something else, because the resolution of that device is till 4 significant figures, or it's till 0.0001, 0.001. Hence, this time the number of significant figures will be 4. Okay. Moving on. Next thing is, however, all zeros appearing in the base, so that has been explained. Thus, in the scientific notation, no confusion arises about the trailing zeros in the base number A. They are always significant. Okay. Okay, now let's move to the fourth example. The fourth example states that the scientific notation is ideal for reporting measurement. But if this is not adopted, we use the rules adopted in the preceding examples. Okay, so again, some rules have only been explained here. Let us look over to the rules. So let's say for a number greater than 1, without any decimal, the trailing zeros are not significant. So this was also been explained here also. So like in this sense, there is no use of the significant or trailing numbers. Okay. Fine. So this thing is explained. Next thing is, for a number with a decimal, the trailing zeros are significant. Again, same thing has been explained here. So if it's 3.200, then 3.200 will have 4 significant numbers or digits. Okay. Fifth example is the digit 0 conveniently put on the left of a decimal for a number less than 1. Like 0.1250 is never significant. However, the zeros at the end of a digit are significant in the measurement. They're just trying to say that this is not significant figure, but this is a significant figure. That's all. Okay. Simple explanation, whatever is written, I just explained to you. So the rule states that this 0 is not a significant figure, but this rule, because the right hand side 0 tells you the precision of the instrument. That's why we will consider that under significant figure, but we won't consider the leftmost under significant figure. Okay. Fine. Next thing states that the multiplying or the dividing factors which are neither rounded numbers nor numbers representing measured values are exact. Okay, and have infinite number of significant digits. Okay, so multiplying and dividing factors which are neither rounded numbers nor numbers representing measured values are exact and have infinite number of significant digits. For example, in r is equal to d by 2 or s is equal to 2 pi r, the factor 2 is an exact number and written as either anything. So here everything will be infinite number of significant digits. Okay, so this is just to explain. This is just to explain that. Even infinite number of significant digits also exist, but this only and only exists. Please read the line. It is written that these are exact. The true value is known. If true value is not known, so you cannot understand or use it for any uncertainty. So just explanation is already given to you. So everything. So this thing written here will have two significant digits. This will have three significant digits. This will have 1, 2, 3, 4, 5 significant digits. But all in all, we know that as the number is exact, it will have infinite number of significant digits. Okay. Okay. Now the final line states that similarly in capital T is equal to small t by n is an exact. Okay. So n is an exact number. So again, n will have infinite number of significant digits. Fine. Let's move on to the rules for arithmetic operations with significant figures. Okay, so how we try to do plus, minus, subtract, divide for these things, we will understand. Then we will try to understand what are the rounding of, how to round off these numbers, and then we can move on to some of the examples. Okay, so that is how our future slides would be. So let us first start with the rules for arithmetic operations with significant figures. Okay. Okay. The first point states that the result of a calculation involving approximate measured values of quantities. What is the meaning of this? That is the values of limited number of significant figures. Okay. So please remember this is again intuitive data only or intuitive information only. Because there was some uncertainty involved, we tried to understand this complete chapter called as units and measurements. Okay. Again, because there was uncertainty, we came up with significant figures concept. If you remember the starting of significant figures, we started with a concept called as there will be some certain digits, there will be some uncertain digits, but significant figures is only defined or we calculate the number of significant figures based upon all the certain digits and only the first uncertain digit, right? All in all, there is an uncertainty associated with significant figures. Fine. Similarly, so not similarly, so aside from this, for the true value, because there was no uncertainty, no error associated with it, so their infinite significant digits were forming. Okay, but it is quite evident that anything which is uncertain, anything which is measured will always have an uncertainty, and because it is having an uncertainty, there is no chance that it will have infinite number of significant figures. Okay, if that measured value is quantifiable, so we'll try to find it depending upon the degree of resolution of the instrument, and depending upon the degree of resolution, we will get some limited number of significant figures which is written. So that complete thing which I just explained was just to explain to you why it is written here as limited number of significant. Okay, fine then. So this thing is done. Let me iterate again. So the rules of a calculation involving approximate measured values of quantities, that is the values with limited number of significant figures, must reflect the uncertainties in the original measured values. Quite evident. It cannot be more accurate than the original measured values themselves on which the result is based. In general, the final result should not have more significant figures than the original data from which it was obtained. Quite evident, if the actual data which was obtained is, let's say, 3.56 meters. Okay, that is the true value. Your answer cannot be more than the true value, right? It cannot be 3.563. The true value is not even 3.563. How can you say that the true value, measured value is 3.563 and the true value is 3.56 only? So, seeing the example, quite evident that the final result cannot have more significant figures than the original data. Okay. Moving on. Thus, if the mass of an object is measured to be, so example, I think there's an example been explained for this only. Thus, if mass of an object is measured to be, say, let's say 4.237 grams, quite evident. 4, 2, 3 are certain numbers, 7 is an uncertain number. Therefore, adding up those, we will get the answer of significant figures to be 4. And its volume to be 2.51 centimeter cube, then its density by mere arithmetic division would be, as you can see, it's 1 point something is written, 1.68804780876 gram per centimeter cube up to 11 decimal places. But you cannot put or cannot provide the answer as this. Why? It would be clearly absurd and irrelevant to record the calculated value of density to such a precision when the measurements on which the value is based has much less precision. So if the values were of much less precision, how can you be so sure that after 2-3 significant digits the answer is correct? If the least amount of significant figures you have is just 2.51 centimeter cube, that is volume, for that is 3, then how can you be so sure that the final numbers which are coming after 3 significant digits would be correct only? Let us say, for example, so all in all, what we are saying is, let us say it is uncertain up to 11 decimal places. What does it mean? It means that the volume is 2.51000000 till 11 times. Similarly, object also is 4.2370000 till 11 times, right? But that is not the case. What if the volume is 2.5199999 and the object mass is 4.2371111? Then it is quite uncertain and the answer might change. But let you put anything after 4.237 and let you put anything after volume and try to find out the answer. You will be certain that if you try to write this answer of what we can say density up to only 2 decimal places, then your answer would be correct. Up to 2 decimal places. I am only asking or telling about 2 decimal places only. Okay, so that is the power, or that is the basic principle of why significant figures concept was being evolved. Okay. Okay, so that thing has also been explained. So it would be clearly absurd and irrelevant to record and calculate the value of density to such a precision when the measurements on which the value is based has much less precision. So everything we have just explained is being written here. So the following rules for arithmetic operations with significant figures ensure that the final result of a calculation is shown with the precision that is consistent with the precision of the input measured value. Okay, so these are the following rules. So now let's follow the rules and then we can go on with further discussion. Okay, so the first rule states that in multiplication or division, the final result should retain as many significant figures as there are in the original number with the least significant figures. Very important. Least significant. Okay. Thus, in the example above, the density should be reported to 3 significant figures. Why? Because the least was for your volume. It was having 3 significant figures. The mass was having 4 significant figures. Okay. So thus, in the example above, the density should be reported to 3 significant figures. Therefore, density is equal to 4.237 grams upon 2.51 centimeter cube, which is equal to 1.69 gram per centimeter cube. Fine. So this thing is explained. Moving on, similarly, if the speed of light is given as 3.00 10 to the power 8 meter per second, as you can see clearly, we no use of this in significant digits. This is only significant digit, and if it is written 3.00, that means we need to understand there is use of this trailing zeros also, hence the number of significant digits will be 1, 2, 3. Okay. So and 1 year is 3.625.25 days has 3.1557 10 to 7 seconds. Okay, so this time, so on calculation, as we took the amount of significant digits in days as up to 5 significant digits, so here also we will take it up to 5 significant digits only. We will try to convert it to seconds. Okay. So now concept here is basically we know that distance is nothing but equal to speed into time, right? Speed has 3 significant digits, time has 5 significant digits. When we are trying to find out the distance here, distance will be having 3 significant digits only. So that is how this explanation is being made. Fine. So this thing is explained, this thing is explained. Okay, moving on. So in addition or subtraction, the final result should retain as many decimal places as there are in the number with the least decimal places. Again, similar intuitive data. For example, the sum of the numbers, as you can see, let us say these are the numbers to be added. Okay, so it's 436.32 grams. So finally, you just need to add this, right? So if you add this simply, so when you add normally, what we do is we add it like this 320, right? So you will add it, you will get the answer as equal to 663.821. Okay, but the least precise measurement is only up to first decimal place. You don't know the exact answer, you are just predicting that these are 0. What if this is 99? What if this is 8? What if this is what if, okay, rest all things are okay. So what if these values are not known? What will you do? That's why the basic crux is that to reduce the uncertainty, to follow the rules of significant figures, what we do is we try to find out these answers for the least decimal places. Therefore, the least precise measurement will be correct only up to 1 decimal place. Therefore, the final answer is 663.8 grams. Okay, so why it is being done, rounding off is done like this, we will try to explain. I will try to explain to you. There is complete rules beside rounding off also. Fine, so this thing is done, this thing is done. Similarly, difference in length can be observed as you can see if you are trying to find this. Okay, so now note that we should not use rule 1 applicable for multiplication and division and write 664 grams as the result in the example of addition and 3.00 and 24 minus 3 in the example of subtraction. They do not convey the precision of the measurement properly. For addition subtraction, the rule says in terms of decimal places only. Okay, so again, it's a very important note. Just try to repeat again and again so you will understand this much more clearly. So one of the method which I generally adopted was in significant figures, because there is little bit confusion always happen. When you are first time reader of significant figures, you won't understand each and every rule very easily. But if you will try to iterate everything, you will try to solve questions regarding this, then it's very easy to adopt. Okay, so practice significant figures and it will be very much easier to adopt all these things. Okay, so that's why, so that is the end. Let me just add this and this thing. Please try to increase read this note again. So this note only says that we should not use a rule number 1. This is a rule number 1 we explained here. Okay, so for application for multiplication division and write 664 grams as the result in the example of addition. Okay, so example of addition and subtraction different, multiplication division is different. Okay, so you do not convey the precision of the measurement properly. For addition and subtraction, the rule is in terms of decimal places only. Okay, so that's how this example is being solved. Let me stop it here only. We will start with the rounding off of the uncertain digits in the next lecture. Okay, so thank you so much. Just the course progress for you. So just the course progress for you. We started the introduction. We went to the international system of units, then measurement of length, measurement of mass, measurement of time, then accuracy, precision of measurement, error in instrument. We also understood combination of errors in this. In this lecture, we are right now on significant figures. I think the last topic of rounding of digits is being left. Then we'll go on with some of the simple examples regarding significant figures, and then we can move on to the next concept, that is dimensions of physical quantities, dimensional formula and dimensional equations, and finally dimensional equation analysis and its application. And that will be the end of your units and measurements. Okay, so thank you so much for listening. Let us meet in the next lecture.